Okay, so if we summarize our previous session, then we have discussed about mercury field in glass thermometer and bimetallic thermometer. Uh, and then these are the advantages and uh, limitations of bimetallic thermometer. So advantages like simple and robust, relatively less costly, can withstand in general about 50% over range, means you can go beyond its working capacity. Their accuracy ranging from plus or minus 0.5 percentage to plus or minus 2 percentage. Now disadvantages, temperature indicated are of limited accuracy because generally the deflection of the beam is non-linear, so we are using only linear portion of the theory. That's why use of linear calibration is limited. Then not suitable for use a temperature above 400 degrees Celsius for continuous duty or above 550 degrees Celsius for intermittent duty. So these are some limitations of dimetallic thermometer. Now their applications. Uh, Bimetallic elements find wide application in simple thermometers in which deflection of element is made to open or close electric contacts in the electrical heat supply to control gas flow or some other fluids. So generally bimetallic elements, this is not the application of bimetallic thermometer as whole, but it is application of bimetallic elements. So it is generally used in the electric context like fuse, right? So when temperature of contact go beyond certain value, then deflection take place, and due to that deflection, uh, that contact release in the electric supply. So generally bimetallic elements, they are used as a safety devices in the electric circuit, right? As a switching device used in domestic oven, electric iron, and the refrigerators. So this is what the switching. It is used as a switching device because once you have selected some temperature range, and if beyond that range it go, then bimetallic thermometer that will, or the bimetallic strip, that will deflect, and there would not be any contact in the circuit. So uh, so electric supply will stop. So these are the broad application of bimetallic element, right? Use as compensator for ambient temperature change in the field system thermometers, uh, and in some watches as a balance wheel compensator. So this is also used as a compensator, as we are not going to discuss field system thermometers due to limited sessions now. But yes, in field system thermometers, bimetallic strips are available as an ambient effect compensator. Like if I give you brief idea, then in liquid field thermometers, as we have seen, uh, three different calibration processes like total immersion, partial immersion, and complete immersion, right? So if thermometer is calibrated for complete immersion, and if you use it for total immersion, then definitely you get variation in the reading due to the ambient effect, because some portion of thermometer that is in contact with the atmosphere, and that will give some variation. So to suppress that ambient effect in field system thermometers, we are using bimetallic strip as a compensator. So this is just an idea about application of bimetallic element in field system thermometers, right? Now we move further with the more popular and more usually find temperature measurement device in processing industries, that is thermocouple. So a thermocouple is a device used extensively for measuring temperature. It is basically working on Seebeck effect. Now what is Seebeck effect? If you look in this diagram, we have two wires which are made up of two different materials, A and B. Now these two wires, they are joined and form two junctions, junction 1 and junction 2. Now junction 1, that is your reference temperature, means T1, and junction 2, that is in contact with the medium whose temperature we want to measure. So T2 is our measuring temperature. So T2 is obtained with respect to T1. So thermocouple measures relative temperature actually, right? So this T2 is in reference with some T1 temperature. So generally junction 1 or the reference junction, that is called as a cold junction, and junction 2 which is your measuring junction, that is called as a hot junction, because T2 temperature always more than T1 temperature. So that's why our reference junction is called as a cold junction, and measuring junction of thermocouple, that is called as a hot junction, right? Now what is basic principle? When you merge two different wires, and if you keep that junctions point at two different temperatures, then there will be a EMF flow. There will be a generation of electricity in the uh, this combination of wire, right? That is called as a electro or which is also called as a thermoelectric effect, because of temperature difference, electricity or the EMF is generated, right? So this is basic principle of thermocouple. You require two different two wires with different materials, and if you keep junctions of those wires at two different temperatures, then EMF will be generated. Now we need to measure temperature in terms of EMF. So initial calibration is required for how much temperature difference T2 minus T1, how much EMF is generated. So that calibration chart or
Sir,
calibration table is required. Yes, Neha.
so why the different materials between
Because single material cannot generate EMF. That is based on the principle. This effect is only possible if you use two different materials. Then and then EMF will be generated. That is one another effect which is called as a Thomson effect. But as we are not going in that much of detail, because if you are using single wire, then according to Thomson effect, EMF will be zero. There will not be any flow, right? So that's why we require two different materials for continuous generation of EMF. Yeah. Now, law of thermocouples. So, thermocouple is used based on three different laws. First is law of homogeneous circuit. Second is law of intermediate temperature. And third is law of intermediate metals. So, first law is about the principle itself. Wait a minute, there is some problem in the presentation. I hope presentation is now visible again on screen. Hello.
Yes.
Okay. Yeah. Thank you. So this is law of homogeneous circuit. So as per law, as principle tells us, like we need to go for two different materials, right? So an electric current can only be sustained in a circuit of single homogeneous metal by the application of heat alone. It cannot be sustained in the circuit of single homogeneous metal by application of heat alone, right? So this is what the Thomson effect actually presented here, right? So you always require M1 and M2 combination, then and then EMF will be generated continuously. Otherwise, you will get only one time voltage surge, but there would not be a continuous EMF generation. So that is what law of homogeneous circuit. So single wire cannot generate continuous EMF flow. Second is law of successive or intermediate temperature. So as per this law, the EMF generated in thermocouple with junction at temperature T1 and T3 is equals to the sum of EMF generated by similar thermocouples, one acting between temperature T1 and T2 and other acting between T2 and T3. So what it tells us, if we are using some material combination M1 and M2, if you keep a cold junction at T1 and hot junction at T2, then that will generate EMF E1. Now, if you now put same combination of material M1 and M2, but now cold junction is at temperature T2 and hot junction at temperature T3, then it will change its EMF, and now that EMF is E2. Now, if I keep cold junction at temperature T1 and hot junction at temperature T3, means from the extreme low temperature to extreme high temperature, then EMF generated will be sum of E1 and E2. So this is actually giving us idea about the linearity of thermocouple performance, right? So if same combination M1 and M2 is used between two different temperature T1 to T2 and T2 to T3, then total EMF between T1 to T3 is equals to these two EMFs, E1 and E2, right? Where this law is helpful to us in thermocouple, it is helpful to generate correction when cold or reference point is other than calibrated cold point. So this is we'll try to we'll try to understand through one example that will give you clear idea. So because what happens, suppose you have calibrated thermocouple for temperature T1 at the time of calibration, because as I told you, we are measuring temperature in terms of EMF, so we required some calibration or some relation between EMF with the temperature difference. So at the time of getting this calibration, suppose cold junction temperature was T1, but now when we are using it for the actual temperature measurement, at that time you are not able to get cold junction at T1, right? You are having some cold junction is some other temperature T2. Then using this linearity law, you can find out actual temperature of uh, medium, right? So this law will be helpful. We'll try to understand it through example. Now, law of intermediate metals. So what it tells us, the introduction of third metal into thermocouple circuit will have no change in EMF generated as long as the junctions of third metal with thermocouple metals are at same temperature. So this law is actually helpful in the manufacturing of thermocouple. How? Let's see. So here we have taken three applications where this intermediate law is helpful to us. If you look first case, right, then this M1 and M2, they are thermocouple materials. So first junction is kept at temperature T1. This is suppose your hot junction. Then this M1 and M2 second junction is not formed. It is not formed, but M1 is connected to some new material M3, and same M3 material is connected to second material M2. And this two junctions point where this M3 is involved with M1 and M2, it's same temperature T3, right? Then now if I form a junction of copper wires at temperature T2, this is our measuring junction point actually, where we are doing temperature measurement. Then if you look, this these two junctions point, they are kept at same temperature T3. Then as per intermediate metal law, there would not be any change in the EMF generated by M1 and M2, right? So this is what this intermediate metal law is helpful to us here, because M1 and M2 materials, they are actually costly material. They are the thermocouple materials, right? But suppose this is the our application N, and we want to display or we want to measure temperature at some other distance. which is having considerable distance from your application. Then we need to go for copper lead wires. Copper is the a very cheap material compared to uh, materials which are used for thermocouple manufacturing, right? So that's why it is called as a lead wires. These are the extra materials. These are called as a extension wires as well, right? So that's why we need to use lead wire for remote indication of temperature. But if you keep temperature of these junctions its same temperature, if you keep both the junctions its same temperature, then as per intermediate law, EMF will not change, which is generated by M1 and M2, right? So law makes possible to use extension wires of a metal different from the thermocouple metal. Otherwise, if you use same material M1 and M2 for long distance, then cost will increase. So this will helpful to us to reduce the cost of thermocouple, right? Now, second application of this law, allow to introduce instrument in the circuit to measure EMF, because temperature is measured in terms of EMF, right? So you need to involve some voltage measurement instrument like galvanometer or any other potentiometer, right? So if you look when you involve measuring instrument, then circuit material is again copper, right? So again that instrument material is different than thermocouple material M1 and M2. But as you include this, and if this junction temperature, that is at same temperature T3, then again EMF generated by M1 and M2 combination between T1 and T2 temperature, that will not change as per this intermediate metal law, right? So we can do accurate measurement without any error of material change. And ideally, this T3 temperature will be the atmospheric temperature, right? Where you make contact of voltage measurement instrument, both the uh, uh, junctions of voltage measurement instrument, then surrounding there we are having atmosphere. So always you get this T3 as an atmospheric temperature, which is same for both the junctions of measuring instrument, right? So again, this law is helpful here, where we can include some testing device for voltage measurement. And last one is about the junction formation, because as you know
सर
we need, yes,
सर फर्स्ट वाला पता ही नहीं चला कुछ फर्स्ट
this
था ना
one,
वो यस
ये
सर
अगर
यस
आप सपोज प्रेशर वेसल के अंदर फ्लूइड है और आप वहां पे टेम्परेचर मेजर करना चाहते हो, तो आप थर्मोकपल का ये जो जंक्शन है उसको इसके अंदर इंसर्ट कर दोगे, लेकिन बाद में उसको बाहर खींच के तो लाना पड़ेगा जहां पे आपको वोल्टेज मेजर करना है. For safety purpose you need to extend it for a considerable distance. अगर ये जो M1 और M2 होते हैं वो जनरली प्लेटिनम और ऐसे कॉस्टली मटेरियल्स होते हैं. लेटर इन नेक्स्ट टू दिस स्लाइड आई डिस्कस सम थर्मोकपल मटेरियल्स, सो दे आर एक्चुअली वेरी कॉस्टली. तो अगर आप पूरा डिस्टेंस कॉस्टली मटेरियल से ही कवर करवाओगे, ठीक है, तो जो ओवरऑल कॉस्ट है थर्मोकपल की वो बढ़ जाएगी. तो कॉस्ट रिड्यूस करने के लिए जनरली हम लीड वायर्स यूज करते हैं. दे आर मेड अप ऑफ कॉपर, ठीक है. तो कॉपर को मुझे थर्मोकपल के साथ कनेक्ट करना है. जहां पे कनेक्ट करूंगा वो टेम्परेचर सेम अगर मैं रखूंगा, क्योंकि इंटरमीडिएट मेटल लॉ क्या बोलता है कि थर्ड मटेरियल आप इंक्लूड करो, लेकिन जहां पे जंक्शन फॉर्म हो रहे हैं थर्ड मटेरियल के, उसका टेम्परेचर आपको सेम रखना है. तो ईएमएफ जो M1 और M2 ने जनरेट किया है वो चेंज नहीं होगा, ठीक है. तो वो लॉ, तो ये लॉ हमें यहाँ पे हेल्पफुल हो रहा है. क्लियर नाउ,
यस
इज इट
सर यस
क्लियर?
सर
या
यस सर
या सो सेकंड में हम दूसरा क्या कर रहे हैं कि हमें गैल्वेनोमीटर या पोटेंशियोमीटर इंसर्ट करना पड़ेगा ईएमएफ मेजर करने के लिए. तो जहां पे इंसर्ट करोगे इंस्ट्रूमेंट, तो उसका भी सर्किट जो होगी उसका मटेरियल अलग होगा. ऐसा कंपलसरी तो नहीं है कि जो M1 और M2 का मटेरियल है वही होगा वहां पे. तो आप इसको इंसर्ट करोगे तभी भी जो जंक्शन फॉर्म होगा वो एटमोस्फियर में रहेगा, और एटमोस्फियर टेम्परेचर आपका दोनों जंक्शन के लिए सेम होगा. तो अगेन this inclusion of measuring instrument in the thermocouple circuit will not change EMF, right? So यहाँ पे ऐसे ही use हो रहा है. And the last one is when you want to form junctions, then you need to go for soldering to form junction. Some joining process is required, and generally we are using soldering, silver material, right? So when you do soldering, then both the junctions or both the wires, they are connected by third material, M3, which is generally copper in solder, right? So again, that copper or that soldering material, that is at same temperature. So again, this additional material will not change EMF of M1 and M2. It will remain same. So this law is again helpful in formulating the junction or in preparation or the fabrication of thermocouple, right? So these are the three applications of intermediate metal law in the thermocouple. Is there any query now in these three laws? Okay, so this is about the characteristics of thermocouple. These are the ANSI symbols of 6 different thermocouples: T, J, E, K, R, S. Now in T thermocouple, T type, generally in industry we need these thermocouples are identified based on ANSI symbol. So if you go to purchase thermocouple, they will ask you which thermocouple you want. So either you should you need to just call its ANSI symbol. Like if I call I want T type thermocouple, then in T type thermocouple, as a positive wire you are having copper, and as a negative wire you are having constantant. So constantant is again alloy of copper and nickel. 57% is copper and 43% is nickel, right? So combination of these two material that form T-type thermocouple. And if you see the temperature measuring range, then it is from minus 200 degrees Celsius to 400. And voltage swing, that is 26 milliwatt. Voltage swing is 26 milliwatt for this change of temperature or in this range of temperature, right? J-type thermocouple, then as a positive material, Fe is used, and as a negative again constantant. Measuring range is increased from 400 to 800. Voltage swing is also increased to 50 milliwatt. E-type thermocouple, it's a chromyl and constantant. So as a positive, now we have chromyl. So in chromyl we have 90% nickel and 10% copper. Measuring range, it can measure from 0 to 982 degrees Celsius. Voltage swing is again more, 75 milliwatt. K-type thermocouple, then chromyl and alumyl. Alumyl is the alloy of these 4 different materials. Measuring range minus 200 to 1200 degrees Celsius. Voltage swing in this range, that is 56 milliwatt. R-type thermocouple, now it is 7% platinum and 30% rhodium alloy. Alloy of these two materials is used as a positive material, and as a negative material we have a pure platinum. Look at the temperature range, it is maximum 0 to 15 or approximately 1600 degrees Celsius. But if you look the voltage swing, then that is too less compared to this previous, right? So it is like a compromise. If you want more temperature measurement, then voltage swing will be less. At the same time, cost of R and S type thermocouple, that is way high compared to T2K type thermocouples because of platinum and rhodium, which are very costly materials, right? S type thermocouple, 90% is platinum and 10% is rhodium. Again, because of reduction of this rhodium, if you look at the temperature range, then that is up to 1400 degrees Celsius, and voltage swing is also reduced. So these are the commonly used standard thermocouples, right? So their temperature measuring range and their voltage swing. Now thermopile. So thermopile, in case in thermopile we are connecting thermocouples in series and parallel connection. So if you look series connection, then in series connection, if you look this A to B thermocouple, so junction 1. Now if you look, the thermocouple N is not connected to A here, but that is free. and from this free end we are connecting next thermocouple of same combination A to B. So we got second junction here, again A to B third. Likewise you can connect n number of thermocouples, right? So, so the purpose is, if these all are connected in series, then voltage swing which is produced, that will be n times the voltage swing produced by single thermocouple, right? So for increasing the response or for magnification of response, for increasing the sensitivity, we are using a series connection of thermocouples, right? And if you look at this A thermocouple is kept in ice bath. Again this AN is kept in ice bath, and from ice bath now we have copper lead wires which are connected to potentiometer for voltage measurement. So this ice bath is your reference junction. So this is cold junction and this is hot junction, which is in contact with the application, which temperature you want to measure, right? So generally thermocouples, they are calibrated at the 0 degree Celsius by using ice bath, right? So this is how the setup is used. Now next is parallel connection. So suppose if you want the average pressure, average temperature in some streamline, then here if you look A and B, this all 1 to n thermocouples, they are connected in parallel connection, right? So this 1, 2, and these are your hot temperature junctions. These all are connected to copper lead wires at reference junction, and reference junction is kept as the calibrated reference junction. It can be a ice bath, which is generally used for calibration of thermocouple, right? And then again we have a potentiometer to get the voltage. So these are the two different circuits where we are connecting thermocouples in series and parallel connection. Now one simple example to understand use of thermocouple. So consider a E-type thermocouple which is to be used for measurement of temperature with cold junction at 20 degrees Celsius. Remember, cold junction is at 20 degrees Celsius. What will be the thermoelectric EMF at 200 degrees Celsius? The following data is the calibration data of E-type thermocouple, right? So if you look, temperature 0, EMF 0, temperature 20, hot junction temperature is 20. Please remember our calibration temperature or the reference junction temperature is 0 degrees Celsius, right? So if you increasing now hot junction temperature, then EMF is increasing, right? So this is the calibration temperature. Now look at the use of intermediate temperature law. What intermediate temperature law tells us? If I want EMF from 0 to 200, means 0 is your reference temperature junction and 200 is your measuring junction temperature. So if I want temperature EMF at 200 degrees Celsius with reference to 0 degrees Celsius reference temperature, then it is addition of EMF between 200 to 20 degree and 20 degree to 0 degree as per the intermediate temperature law, right? So so now if you look this table, what we want, what will be the thermoelectric EMF at 200 degrees Celsius? So if you look, as per intermediate temperature law, we got this relation. Now I want thermoelectric EMF at 200 degrees Celsius when we have cold junction at 20 degree Celsius. So we want this value, this EMF, right? Now E 0 to 200, that is available from the calibration table. So if your reference junction temperature is at 0 degree and hot junction is at 200 degree, then EMF will be 13.419, right? So that value is available, this value is available from calibration table. We want EMF generated at 200 degrees Celsius when cold junction is at 20 degree. So again this E 20 when cold junction it is 0 degree, that is available from this calibration table 1.192, right? So E 200 to 20, that is nothing but E 200 comma 0 minus E 20 comma 0, right? So we take difference between these two, then this will be the EMF generated if hot junction temperature is 200 and cold junction temperature is 20 degrees Celsius, right? So this is how we are getting this thermoelectric EMF. Any question or any query? This is the application of intermediate temperature law. Very simple. Okay, so I move to next question. Share again, there's some issue in the presentation. Share it again. I hope this slide is visible now.
Yes, sir.
Yeah. So again, similar example, the hot junction of a chromial alumyl thermocouple is connected to potentiometer whose terminals are at 24 degrees Celsius, right? The potentiometer reads 25.76 milliwatt. What is the temperature of thermocouple hot junction, right? So if you look, the cold junction temperature during this measurement is 24 degrees Celsius, right? And this EMF is generated when cold junction is at 24 and hot junction is at a particular temperature. Now if you look, this calibration table is available for reference junction or cold junction at 0 degrees Celsius, right? Then again we apply intermediate temperature law, like EMF from 0 degrees Celsius cold junction to actual hot junction is equals to EMF for 0 degree reference junction to 24 degree hot junction plus EMF for 24 degree reference junction and actual hot junction. So this relation we have based on uh, intermediate temperature law, right? Now this, both the values, they are available from table, right? So 0 to 24 is 0.95, it's 0.95, right? Plus 24 to hot junction EMF, that is 25.76, that is available from potentiometer. So 25.76, if you do total you get 26.71. now go to this chart. 26.71 is very close to 26.72. so looking to this, we can say temperature of hot junction is 488 degrees Celsius. So that is what, how we are getting the actual temperature of hot junction. Is it clear?
Yes, sir.
Okay, so this,
सर
yes,
हेलो सर
yes,
सर
yes.
लास्ट में आपने माइनस क्यों किया था वो एक पता नहीं चला तो लास्ट वाला क्वेश्चन था ना
Here
उसमें
in
यस
this question,
सर
हाँ,
यस सर
देखो आपका अगर कोल्ड जंक्शन 0 डिग्री पे हो और हॉट जंक्शन 200 डिग्री सेल्सियस पे हो, तो अगर आप कोई भी इंटरमीडिएट टेम्परेचर, सपोज मैं बोलता हूँ कि 30 डिग्री मैंने लिया फॉर एग्जांपल, कि अगर मैं थर्मोकपल का कोल्ड जंक्शन 0 डिग्री पे रखूं और हॉट जंक्शन 30 डिग्री पे रखूं, तो जो ईएमएफ आएगा वो प्लस, नाउ इफ आई पुट thermocouple cold junction at 30 and hot junction at the measuring temperature, then that will give me some EMF. ठीक है, तो दोनों EMF का अगर मैं टोटल करूंगा तो मुझे कौन सी टेम्परेचर रेंज मिलेगी? 0 टू दी हॉट जंक्शन. इज इट क्लियर? जैसे यहाँ पे आप देख रहे हो, जब मैंने कैलिब्रेशन किया है तो T1 जो मेरा है दैट इज कोल्ड जंक्शन, यानी 0 डिग्री सेल्सियस. 0 डिग्री पे ही कैलिब्रेशन होता है थर्मोकपल का. ठीक है, तो अब जब आप एक्चुअल में यूज करने जा रहे हो तो आपका T3 जो है वो आपको मेजर करना है. ठीक है, तो T3 मेजर करने के लिए आपको कोल्ड जंक्शन कुछ फिक्स करना पड़ेगा. आपके पास जो कैलिब्रेशन टेबल है वो 0 डिग्री कोल्ड जंक्शन के लिए है. ठीक है, लेकिन आप जब T3 मेजर करने जा रहे हो तब आपको कोल्ड जंक्शन टेम्परेचर T1 जितना नहीं मिल रहा, वो T2 जितना कुछ मिल रहा है, यानी 0 नहीं मिल रहा, आपको 30 मिल रहा है. तो आप 30 के ऊपर मेजरमेंट कर लो, कोई प्रॉब्लम नहीं है. ठीक है, तो 30 कोल्ड जंक्शन और सपोज 200 हॉट जंक्शन के लिए आपको कुछ EMF मिलेगा. दैट EMF इफ यू ऐड फॉर EMF फॉर कोल्ड जंक्शन 0 डिग्री एंड हॉट जंक्शन 30 डिग्री. ठीक है, ये दोनों को अगर आप ऐड करोगे तो जो आपको EMF मिलेगा वो क्या रिप्रेजेंट करेगा, कौन सी टेम्परेचर डिफरेंस रिप्रेजेंट करेगा? 0 से लेके हॉट जंक्शन का. ठीक है, ये क्लियर हुआ, ये प्रिंसिपल क्लियर हुआ?
यस सर, यस
ठीक है, तो
क्लियर.
हाँ, वही प्रिंसिपल फिर हमने यहाँ पे यूज किया कि मुझे जो 200 डिग्री सेल्सियस चाहिए दैट इज विथ रिस्पेक्ट टू 0 डिग्री सेल्सियस, राइट? अब आप यहाँ पे देख रहे हो कि जब मैं एक्चुअल में यूज कर रहा हूँ मेजरमेंट, तब कोल्ड जंक्शन जो है वो 20 डिग्री पे है, वो 0 डिग्री पे नहीं है. ठीक है, तो EMF 0 से 20 is equals to 20 to 200 और we can say 0 to 20 and 20 to 200. ठीक है, अब मुझे EMF चाहिए 200 डिग्री सेल्सियस के लिए जब कोल्ड जंक्शन हो 20 डिग्री, यानी कि मुझे ये EMF चाहिए. ठीक है, अब 200 का EMF जब कोल्ड जंक्शन 0 हो और हॉट जंक्शन 200 डिग्री सेल्सियस हो तब का EMF मुझे कैलिब्रेशन टेबल में से मिल गया, तो वो मैंने ले लिया. अब जब कोल्ड जंक्शन 0 हो और हॉट जंक्शन 20 हो, वो भी मुझे कैलिब्रेशन में से मिला, टेबल में से मिला, तो वो मैंने ले लिया. दोनों का अगर मैं सब्ट्रैक्ट